Okay, so we proved a theorem about removing spheres from spheres, but now we want to discuss an application where we remove spheres from a Euclidean space instead. So the theorem is like this. A continuous injective map. So n is going to be at least 2 here. So Rn, a plane, or R3 or something, or bigger than that. And we've got a continuous map in from the n-1 sphere. So we're going to form the complement here, the Rn, and remove this f of Sn-1. So I'm going to claim this has precisely 2 path components. And so one of them is going to be bounded and the other one's going to be unbounded. So you should think, in that case, n is 2. So Sn-1 is a circle. So here you've got an injective map from the circle into the plane. So the image of an injective continuous map like that is what's known as a Jordan curve. And the claim is that that has an inside and an outside. The inside is the bounded component and the outside is the unbounded component. And that's kind of very easy to believe in cases where f is some kind of nice simple thing that you can easily draw. But f could have an extremely large number of squiggly bits, in which case it would kind of be hard to tell whether you're inside or outside. And it could also kind of have sort of fractal sections or things like x sine 1 over x, which oscillates infinitely often. It could be very complicated, in which case it's not so easy to see that this is true. And it's kind of very fiddly to prove this without homological methods, but with our homological tools we've now got available, we can do it in a fairly streamlined way. Okay, so it'll be convenient. We can well, so this is going to be compact, right? Right, because Sn-1 is compact, and so it's going to be bounded and closed. Okay, and so we can multiply by it doesn't really change anything if we just multiply by a small constant, and we can assume that that the image of this is contained in the open ball of radius 1 around the origin. That will be convenient. So we we regard kind of Rn as Sn with a point removed by stereographic projection. And if you look at the formulae for stereographic projection, the way this works, then this OBN corresponds to you think of A as being the North Pole, say. This corresponds to the bottom hemisphere. Okay. Okay. So so let's put A plus is the top open hemisphere. So this A is going to your North Pole. That's going to be contained in A plus. Okay, so we know by our last kind of big theorem that the homology of Sn with f of Sn minus 1 removed, that's the same as the homology of S0. Okay, so all you've got is 2 copies of Z in degree 0, and all the other homology groups are true. And so it follows that so this has precisely 2 components. Okay, so okay, so this point, remember, the point little a, the north pole, as if you like. So that's certainly a point which doesn't lie in f of Sn minus 1, because f of Sn minus 1 is in your Rn, which is Sn less a. So so we've got this point A in this complement, and we let capital A be the corresponding path component, and we let B be the other one. Okay, so what do we know about A and B? Well, firstly, as we said, that this is Fsn minus is compact, it's bounded and closed. So this Sn with that removed, that's an open subset of Sn, and so the path components of an open set are open. Okay, so these are both open subsets of Sn. Yeah. Now we know that this complement that we're looking at, that's the disjoint union of A and B. Therefore, homology of A plus the homology of B is the homology of this complement, which we know is just Rz squared. So these two sets, they must be acyclic as well. Okay, so so we've got this complement. It's written as a disjoint union of 2 acyclic open sets. But we didn't. This was the complement in Sn, and we wanted the complement in Rn instead. Okay, so let's think about that. So let's put A prime is this is this component A, and I just remove the point A. So so that's open, and we take Rn and we remove Fsn minus 1. That's the disjoint union of A and B. Yeah, here B, remember, is contained in the so yeah, well, let's just say B is path connected. And so if we can prove that A prime is path connected, then that will mean that it's we've proved most of what we need to prove, right? Then A prime has to be the other component. Okay, so this A prime here, I want to claim that that's path connected. Now remember, because A prime, this was this open set A, and I've removed a single point from it. Okay, so so this should be kind of believable, right? There, Sn, remember, was at least 2. So we've got this kind of two-dimensional situation, and then we've got an open set. We remove a single point. That's not going to prevent it. That's not going to break it and make it disconnected. But it's a little bit fiddly to prove that kind of directly in a rigorous way, kind of using actual paths. So we're going to give a homological proof for this fact that A prime is path connected. Okay, so remember, so A plus is the upper hemisphere. Okay, and we arranged our f so that f of Sn minus 1 was completely in the lower hemisphere. So this is all contained in Sn with fSn minus 1 removed. Right, and this is just a hemisphere, so it's kind of obviously path connected. So that point A, that's our north pole, right? That's certainly contained in A plus. Therefore, A plus is contained in the path component of little a, which was by definition the set capital A. So now what do we know? We know that okay, so from that it's clear that if you take A plus union A prime, right, A prime you just removed A, but when you take the union with A plus you put the little a back in, so that's just all of A. A plus intersect A prime is the hemisphere hemisphere minus the point, and that's path connected. Okay, so there, nothing. It's very straightforward to check, and yeah, and we know that, and also A plus, and this we know is acyclic, and A plus is also contractible. Okay, so A plus is contractible. Okay, so so if we look at, we've got a Mayer-Torres type sequence. Okay, so we've got H1 of the union. Okay, and that's 0 because it's acyclic. Going to H0 of the intersection. But this intersection we know is path connected, so this one is Z. Going to H0A plus and H0A prime. And so here you've got a Z and a H0A prime. And then you go to H0 of A, which is just the integers. And so it's not very hard to see from this that this forces H0A prime to be Z. So yes, exactness. Yeah, I mean, if A prime wasn't connected, you'd have several Z's here, and it wouldn't be possible for this to be exact. So so this A prime is path connected. Therefore, A prime and B are path components of Rn with f of Sn minus 1 removed. So we know that B is contained. Well, we know that A prime contains A plus. So that implies that the B, or A prime contains A plus with the north pole removed, and so that implies that B is contained in the lower hemisphere. Which corresponds to the open ball in Rn. So that means that B is bounded in Rn and A is unbounded. So A prime is unbounded. Okay, so that proves this generalized Jordan curve theorem. Any copy of Sn minus 1 in Rn divides it into two components, which is, as I said, highly believable, but very difficult to prove without homological methods.